it's criminal to me that something so simple, something that is like the foundation of 3D graphics in video games, is not just in every slicer. How's it going? You can call me Crimson, and I wanted to talk about 3D printers today. Wasn't a plan for this channel at all, but I did recently acquire my first 3D printer, which was a Bambu Labs A1, and as I did lots of research, and I just so happened to buy it right before the recall, but I haven't had any issues with mine, but I became familiar with CNC Kitchen as a channel, and he recently came out with, stop using calibration cubes, a video about the fact that calibration cubes are generally not as useful as one would think. And that's totally true. No problems with the video, but I felt like I could add some additional input and math and trying to deal with problems. So nothing that Stefan said was wrong, but I felt like there were some gaps. So namely, the first thing is the video almost entirely talks about skew in the XY plane, which would be like the print bed itself, this way. But there's actually two more planes. There's this plane, which is like on my printer, is the X and Z plane. And then there's this plane, which is the Y and Z plane. And the printer can be skewed in any one or all of those planes. So in the XY plane skew, right, we're talking, I've got Blender here, and we're talking about skew that is going to skew the cube in this kind of direction, kind of going up and to the right or up and to the left and so forth. But you can actually be skewed on these faces or these faces. And I know they're not very easy to tell apart other than the axes here, but that is the idea. So that is the first problem, is that we can correct skew in the XY plane, and in fact, it's the easiest plane to correct skew in. So it is, tangible, it's easy, or easy enough. But there are two other planes that have other implications on the quality of prints. As the print head is moving up in the Z direction, and we have skew in relation to Z, then we're necessarily shifting layers, right? We're leaning the part. We're making the part should be straight up and down, but it's doing this as it goes up. And that is also a problem. Now, I don't think most prints tend to be, people print very tall, but it's possible. And so it isn't necessarily negligible. So we shouldn't ignore it as a problem. The other thing that is in there, and not to say that it was being ignored, it just is something everyone should be aware of. It's more than that. So it is something worth paying attention to. The other thing is that he mentions that if you don't have a more open platform printer, you probably are, SOL on your ability to find a way of dealing with it. If your slicer that is available to you doesn't have skew compensation as a feature, which we're going to get into why I think that is inexcusable. Every single slicer should have this as a feature. It is actually so easy to do, which is what we're going to get here in Blender. But the other fundamental thing is that I am one of those people who have a Bambu Labs printer, and it isn't necessarily as open a platform as others. So as far as firmware and warranty and all of that, so my options are limited. And Stefan does mention that you can do a post-processing step, that people do have scripts to do post-processing. And for closed platform printers, there's no guarantee that one script will always work for whoever's printer you might have, right? If formatting is different. So it is, that compatibility problem. And that's talking about post-processing. So I wanted to present at least a naive approach to pre-processing a problem. Obviously, it would be better if the slicer had skew compensation, but for now, the one that I'm using, Bamboo Studio, right, Bamboo Slicer, does not have that. So that is a problem. Something else that I personally have already experienced is the dimensional accuracy from the different axes for my printer are not the same. So that causes a problem for technical parts where I've printed a 100 millimeter by 100 millimeter square, but one side is 99.75 and the other side is 99.2. So just a unilateral XY compensation scale that applies to both the same is insufficient. I can't correct them because I can't correct them separately and they are different. One number does not make it correct in both directions. So that is also wholly useless. But we can actually do scale correction for a specific material on our printer in the same transformation that we do with skew, and we can treat each axis separately the same way. So if you have a scaling problem, a dimension problem, not necessarily skew, but literally that one side is just behaving differently, then this also is a solution. I did put together a spreadsheet. It does compute this for me. I am still iterating. I'm not going to be releasing it. Part of that is also I agree with the sentiment from Stefan about Atom. The calibration cauliflower is awesome. I did not use it. That is primarily because I needed a print that was going to be compatible with vertical printing to measure those other planes, right? This can print flat like this with no support, but printing it like this is a problem. So I needed to come up with a solution that would avoid supports while letting me get useful measurements. That resulted in many iterations. That resulted in a stack of paper like this. These are failed. These are different geometries, different ways of doing math that either were going to be too complicated, too much work for the everyday person to deal with, or just failed bad designs. And what it boils down to is this: 3 pieces of paper discussing the math for each plane of correction. It's pretty straightforward. I'm leaving out a lot of algebra on those pieces of paper, but nonetheless, it's pretty straightforward. So what are we fundamentally doing? What is the fundamental problem? We're going to get to Blender here. So if we have a printer is inherently a transformer. So we have a set of bases that we work with in like Blender here, where we are expecting I, J, and K, or I hat, J hat, and K hat, which are the orthonormal basis vectors that we work with every day. That's 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. Those are I, J, and K. So those are what we define when we say I'm like at 2, 1, 3. We're really saying it's a linear sum of 2 copies of I plus 1 copy of J plus 3 copies of K. That's how we get from the origin to 2, 1, 3. So that is where we're working with our models. And the problem, the reason we have skew from our printer, is that our printer, because it's not a perfect structure, it's not a perfect system, it doesn't work with the same basis. So we're telling it to go to 2, 1, 3, but it's not adding I, J, and K. It's adding some different variation where maybe I isn't 1, 0, 0, it's 0.98, 0, 0. Or maybe it's skewed, so it's not 1, 0, 0, it's 1, 0.1, 0, which just introduced an XY plane skew. Whereas we move along the x-axis, we actually are going to add drift in the y direction. So these are defects in our ability to make a perfect representation of an orthonormal basis. We can't necessarily make it be, we can't make perfect stepper motors, we can't make perfect linear rails and perfect belts. We can get as close as we can, but we can't really get them perfect. So we can, though, because that is fundamentally, I'm going to try to keep linear algebra out of this discussion, but what that printer is representing is a change of basis, which is a type of linear transformation that is also something called isomorphic. If you're interested in any of that, what that means, I highly recommend 3 Blue, 1 Brown's Linear Algebra video series. Fantastic. And they will go specifically over what linear transformations are and what change of bases are. I don't want to go into the physical math that deep, but suffice to say, it boils down to some matrix math we can do. So what is happening is, let's say our printer is doing the correct scale of x, but it's skewed. So maybe we have I'm going to be exaggerative so we can see the change, but maybe our x vector, our I hat on our printer, our I hat equivalent, is actually not 1, 0, 0, but it's 1.25, 0. And then maybe y is perfect. There's nothing wrong with y, so it's 0, 1, 0, or j hat. And then maybe z, for now, is also perfect, so it is 0, 0, 1. What will happen is, this is our model, this is our cube, but what happens is, I need my button here, what happens is the printer takes our instructions of going to each point, like 2, 0, 0, and it applies that math, that summation of adding i's, j's, and k's with its version of I, which does this to our cube. Boom. That is no longer a cube. We have a very badly skewed cube. It still is perfect in the other planes, but in this plane, it's wrong. So when we look at this plane, it's still correct. These vertices in this plane are correct. These vertices in this plane are correct. But when we look down, top down, that is not a square anymore, right? And I'm being a little bit, it's imperfect. If I snap, right, this is a square. That is, this edge here is a square. And if I rotate around, that is also perfectly a square. So this is the zx and zy planes. That's what we're looking at. And they have not been changed. But if we look from down the z-axis, then we are looking at the xy plane. And we have a diamond. We have a parallelogram. So that is our skew. This can be undone. So we can use the inverse of that matrix to get back what we wanted. So if we take this and we go back the other way with negative, right? If we take this and we just go back the other way, we're going to get back our perfect cube. This is a simple inverse matrix. So right, this is what our matrix here looks like. And I'll explain why we only have this. This bottom row here does not matter. Doesn't matter. It's for Blender for translation, moving around in the world space, as opposed to the center of the object and rotating it. So this is irrelevant. That's always going to be 0, 0, 1, 0, 0, 0, 1. And then this ideally is 1, 1, 1, and then 0, and Q and R also zeros. We want this to be an identity matrix. If what our printer did was a perfect printer, its transformation matrix would be the identity matrix. It would be a 1-to-1. It would not change the basis whatsoever. It would stay the same. So now, if we go backwards, we change this to the inverse matrix, we're actually going to get back our cube. Boom. There it is. And so just one button, and it's undone. And this happens to be a property of inverse matrices and just matrices in general, is that they have a property of, the commutative property of multiplication. So they can be multiplied back and forth, and they can have inverse matrices. So that means that we can pre-multiply the inverse transformation, this -2, 5. So what's going to happen is I'll do it again. I'll apply this transformation. And now our parallelogram is facing the other way. We've transformed it backwards. So we started with our cube. That's the model we want. Then we pre-multiply by the inverse of the transformation matrix we'll have to solve for our printer. And then we can then run it through the printer. So this looks now with a positive 0.25. That's what our printer is doing to our parts. And then when it runs through the printer, we end up with the thing we wanted because we pre-undid what the printer is doing to our parts. And so we can pre-multiply the inverse. And the idea there, right, just like, 1 over 3 is the inverse, the multiplicative inverse of 3. So 3 times 1/3 is 1. 4 times 1/4 is 1, right? The multiplicative identity, right? So we can pre-multiply by 1/3 so that when the printer multiplies by 3, we get back what we wanted. So say you had some crazy printer that was really shrinking, like its units were off for some reason, right? And so you actually had like a scale problem, a huge scale problem. So we're going to say x is actually 0.5 and y is 0.5 and z is 0.5. This is an unskewed printer from our math here. There's no skew, but the printer is printing everything at half scale. And I want you to just think about why that is if you're unfamiliar, but we're actually going to be multiplying by 0.5 on all of the positions, the lengths of all the vectors unilaterally. So we're going to end with a cube that is half size. Well, that's a problem. We don't want that. I mean, this is a problem that's not realistic, right? Something else is way wrong with your printer. But if that was happening, you don't have to necessarily fix the printer, right? You know this. If you mess with printers, you know you can just scale parts ahead of time so that they end up where you want. And that's the same thing here. So we can actually just say, well, if we just multiply by 2 first, which we just undid, but if we do that again, we get a big one. And that's the inverse of that 0.5, 0.5, 0.5. So if we multiply by the inverse first, and then we multiply by this so-called halvesies printer, what we end up with is the cube we want. And that's the principle of what we're doing. So what we need is a way to get there. And so we have to measure the skew of our printer. I am a person that is very much after precision. I like getting things as precise as I can, and preferably in the lab. I want to get things as precise as I can through the raw math, through the principle of the measurement, as opposed to getting lots of repeated measurements. Right? I want to minimize error by making a good experimental design instead of brute forcing it with, some kind of, micrometer or average value standard error from like 10,000 measurements. So I first made this, and again, this is going to make sense later when I pull those ones out, but this is an octagon, and the octagon is really about 2 squares. It's about a square here and a square here. Right? I rotated the square 45 degrees. They're in one print, and they represent a set of vectors that we can use to reverse engineer the matrix that we're seeing here, specifically S. This got printed in the XY plane. Now, this is where we're going to get into why is there no values, no variables other than Y. That's because we are going to lock the rotation. This matrix doesn't just have to do skew, it can also rotate stuff. And we don't want that free variable of rotation to exist. So we're going to say, for me, I said the y-axis, the bed slinger axis, is locked in place. There's nothing wrong with it but scale. So y can either be 1 if you don't want to include scale, or you can find what y is for your printer, what the scale is, to be able to correct for scale problems that is holistically inclusive. It includes the scale of problems with the stepper motor in the axis and shrinkage. So that's the first step. And so that means we can actually very easily calculate what y should be by measuring this distance here, this upper one. I don't know if that's showing up so good, but this one right here. So this square, that's just a direct vertical measurement. And then this diagonal of the related rotated square is also straight up and down. I won't go into all of them, but that is the idea. We have a set of vectors that we're measuring. And then that boils down to let us calculate y first, then s. And knowing s, we can calculate x. Together, the magnitude of that vector is the scale. So then we can then scale that to scale the x direction. And then we do the same thing that's a little bit more involved for q and r. And we're saying that that vector of z is the whole, all of the skew is related to z. Just trust me that that's okay. There's math reasons why that's okay. And this just makes it go from a 3x3 or a 9 variable problem, and it lets us reduce it down to a 6 variable problem, where we get y for free, and then x is a byproduct of solving for s, and then s only depends on a couple of measurements. So it's going to be dependent on this diagonal, and well, all 4 diagonals, but these diagonals all represent the same fundamental vectors, so, or related vectors. So we can solve for them, and then we can compute that, and then we can compute for q and r. This is the actual file where I was originally doing this, and these are the values of the skew. And so this represents, this x and s value represents about a 0.33 degree skew for my xy plane. And then y, this is the inverse matrix. So this is the undoing part. The magnitudes are similar, but so if you inverse this, you'll actually, if you were to type this matrix out, you'd actually find and do the inverse, you would find what my printer is doing to my prints. And you'll see that q and r are non-zero. So I have about a 0.3 degree skew in the xy plane, and I have a 0.2 and a 0.14, I think, degree skew in the 2 vertical planes. So not as bad, they're not as bad, but they are skewed. And I was able to correct them. And how I did that was by printing these. Part of the reason that I went with the octagon is that this octagon can print with no supports. And you'll see, we're very clearly seeing this rotated square. The other square, the standard square, doesn't fit. So that's a problem because it would need support, right? That's why it doesn't work. So we only get this one square. So we lose precision, but at least we can print these. And these do take some time, and I have problems with this. The main problem, we're getting to the end of the video here, but the main problem is that these squares, like this print, is very flexible. So getting a reliable measurement is really bad. The benefit of this print is that in every direction that on the diagonals, which are the most important measurement, they are strongly supported. So there isn't a lot of give or stretch in when you are measuring with the calipers. That is not true here. And so these have a little bit more flex than I would like, and I think that I can fix that, but right now it is not perfect. And I also don't know how people would feel if I presented a different solution, but this is why I didn't use the cauliflower, is because it can't do this. It looks more like this. So it's useful for the XY plane, and it's useful for scale, but it does not work for the planes involving the z-axis, and this does. And this is just a cauliflower on steroids for specifically measuring skew, while keeping the math relatively straightforward. And when I say straightforward, I really do mean straightforward. All of the math for some of this literally boils down to something as simple. Oh, come on. Fine. Just trust me. We have c squared minus d squared divided by 4a, where a in my spreadsheet is just y. So they are very simple calculations, and it's a very simple function to compute s. That's how you get s, right? And then x is just, standard circle. It's a square root related to the radius minus s, and you get x. So, squared, those terms are squared. So it is very simple. The math is very easy and understandable. And if people are interested, I can go happily make a video about the actual math, what this page means for solving the XY skew, and then this page solves for the ZY skew, and then this page solves for the ZX skew, and so on. So it's really just linear algebra. And to finish out this video, the idea here is it's criminal to me that something so simple, something that is like the foundation of 3D graphics and video games, is not just in every slicer. Why is such a simple thing where you can just measure this property of your printer and just put it right there to correct for it? It should just be in there. Instead of pre-processing and having that caveat of the rotation, you instead can just have it such that you would have the slicer set up your bed, set up your print, and then right before it goes to actually start slicing, apply the transformation from the matrix you provided to rotate the vertices to skew them correctly in the opposite direction. And then you end up with everything being transformed in the way that you want to print it, and then check that, and then slice. And then, because it's possible after the transformation, it would push like out of a boundary, etc. So you would set them up, skew, counter skew, and move on, and slice. That's it. That's the whole thing. And it's one matrix multiplication. That's it. So I don't understand. So my camera is gonna stop recording here. So I've got to call it. But thank you for watching. Hopefully this made some sense. And if you are interested, let me know. And I will go into far more detail, more like a lesson, especially if people are interested in math. But like I said, 3 blue, 1 brown. Anyway, thank you guys again. You can call me Crimson. And this channel is going to be mostly around computer programming and stuff. But I just thought that I would add my 2 cents in here because I saw an opportunity to help the 3D printing community. Have a good one.